step in Genrix's algorithm that we need to analyze in order to analyze this question. And what we're going to do now is we're going to use those tools we developed to actually analyze generalized eigenvalue and generalized eigendecompositions. And just as a quick reminder, let me remind you about the condition number and what it controls, as well as I'm going to state Gershgorin's theorem again because we're going to use it. But the condition number of some matrix was just the ratio of its max eigenvalue to singular value to its min singular value. And the key result that we showed was that if mx equals b, so b is the true, mx equals b is the true linear system we wanted to solve, and instead we were given some noisy approximation of the right-hand side, and we solved it nonetheless, then what we showed, it's a very simple bound to show, was that the condition number controls how much the relative error can increase. So we showed the following type of bound. That if we take the relative error on our right-hand side, so we wanted b, but we had b tilde, and so we look at the magnitude of that norm divided by the norm of b itself, then the condition number controls how much we can expect the relative norm in our solution to be off from the right answer. So that was the first key result, was the statement that condition number controls how robust the linear system is when you solve it, with not necessarily exactly the correct right-hand side. Now the other result we needed was Gershgorin's theorem, which had this really nice geometric view to what happens to eigenvalues. So what we said was that, and we proved it, we proved that the eigenvalues of m are contained in a particular union of disks. So they're contained in union from I equals 1 to n, if it's an n by m matrix, of the disk centered at mii, so one of the diagonal entries, whose radius ri is given by the sum of the magnitudes of the off-diagonal entries. So this was the way of thinking about, if you had the identity matrix and you take a small perturbation of it, it shouldn't change the fact that it's still invertible and that its eigenvalues are close to 1 regardless. But there's actually a stronger statement, which I just asserted, which we're also going to need, is that there's a nice condition that happens when the disks are disjoint. That what you hope happens does happen, that each of those disjoint disks, n of them, really does contain one and only one eigenvalue. So that was the key point. Now the way that we're going to use this is if you think about m as arising in Genrix's algorithm, where it's a matrix where if we had exactly m, we'd be in great shape. But if we instead have m tilde. So the way that Genrix's algorithm works is that if we have m, well, the conditions on Genrix's algorithm ensure that m is itself diagonalizable. That's the way that we set up Genrix's algorithm. But one of the most basic questions is when we add a perturbation to m and create m tilde, what are the conditions under which we can still say m tilde is diagonalizable at all? So that's where we'll really need to invoke this other part in Gershgorin's theorem. It follows almost immediately from this, plus a sort of continuity argument about the eigenvalues. Because what you can think about doing is you can think about taking the diagonal matrix with mii along the diagonal and slowly scaling in what the error is. And the disks become larger and larger, but the eigenvalues can't really jump out of one disk into the other. So it follows by simple continuity arguments. But now, returning to this eigendecomposition problem, what I claimed the main key for analyzing how stable our tensor decomposition algorithms are really revolves around how stable are eigendecompositions. what are the conditions under which an eigendecomposition is stable. And what we're going to do is we're going to say that, throughout, we're just going to say m equals u d u inverse. So this is our true diagonal matrix, diagonalizable matrix that we'd like to have. Instead, what we have access to is m tilde equals m plus e. Now, there are going to be two parts to this analysis. And I don't want to get too involved into like what's the tightest bound, but you want to focus on the qualitative issues of if I have the freedom to drive the error down, can I drive the error in my estimates down too? And is there a polynomial relationship between how much I need to drive this error down to drive my estimates down to the truth as well? You should think about this E as the way it's going to come up in our analysis is it'll be associated with the fact that we want to approximate the moments of some distribution, but the best we can do is we can take many samples and take their empirical average. As we take more and more samples, E is going to drive down in a polynomial rate, and we want to show that if we find some decomposition U tilde, that's also going to converge to U at some good rate as well. So this is the sense in which we really have a polynomial time algorithm, is analyzing its sample complexity as well, but just focus on the qualitative issues. So part one of this is we first want to say that under the right conditions, m tilde is diagonalizable. And we'll see what conditions exactly we need when we start to prove this. And part two is we're going to study perturbation bounds for the eigenvectors themselves, because those are the factors that we're interested in recovering via tensor decomposition. So is there any question about what this game plan is? All right, makes sense. So let's do part one. So, yep.
So what is the property that we actually want to show exactly? That like that you have to do recover this?
What we want is we want that if we take an eigendecomposition of m tilde, we want some reasonable conditions under which the eigendecomposition of m tilde, its eigenvectors u tilde, are close to the true eigenvectors u. That's what we want. But the way to think about this is that you have the freedom to drive E down. That's the thing in which you're allowed to take more samples. You can't make it, exponentially small, but you can make it as polynomially small as you want because you're taking a polynomial number of samples. So we're interested in the qualitative question about if we can drive it down at a polynomial rate. What does that say about the rate of convergence of u tilde to u? Now there are caveats here because you're going to need to assume things about, let's say, the condition number of u, or things like the minimum separation between eigenvalues in D. If you think about it qualitatively, if D has some repeated eigenvalue, then the eigendecomposition itself is not unique because, there's some eigenspace with two eigenvectors, and then a really tiny perturbation could break that tie and completely change what's going on. So those will be the two conditions that we actually need, are conditions on the condition number of u and the separation between the eigenvalues. But if you think about Jenrick's algorithm, what happened was we hit it with two random vectors A and B, and we could use sort of anti-concentration properties to say that it's not that likely that they're extremely, extremely close. So there'll be a lot of things which we're going to assume are reasonably bounded, but there's the qualitative question of if all of that stuff happens, which it should anyways, what does that say about our estimates in terms of their convergence rate? So that's the main question. So here there's going to be a trick. There's one key trick, which we sort of use again and again, is, we want to first show that m tilde is diagonalizable. So the way that we do it is we just exploit this crucial property. what if we took the true eigenvectors that we're looking for and hit it with U inverse on the left and U on the right? What I claim is that this set of eigenvalues is the same. Can anyone tell me why?
U inverse. U transpose is identity.
Even if they're not orthonormal, that's a good test case. If U is, an orthonormal matrix, then it would definitely be true. But in general, it's true too, because these are similar matrices. That's just an invariance property of eigenvalues, is that they're the same under multiplying, conjugating by U inverse and U. If you think about it as if I put in M here, right? Well, then if I conjugate by U inverse and U, I get the diagonal matrix, which we just read off from the diagonal what its eigenvalues are, and that is the same set of eigenvalues here. It's a more general property that whenever you conjugate by an invertible matrix, you have, these are called similar matrices, and hence their eigenvalues are the same. But now this is great, because what we can do is if we take U inverse times M tilde, then we can write it out in the obvious way. Right? And this is the key point, is that as you're driving E down, it's, whatever the condition number of U is, if that's bounded, this term also gets driven down. And hence, how are we going to finish this? The answer's on the board someplace. Verschoren's theorem, right? Now, there's a sort of key point here. So let me call this, F, right? And what I'm really saying is that the max entry in F, well, it's achieved by some, you can think about it this way. As you take your matrix, and you take some quadratic form on it with basis vectors. So whatever the largest entry is, you can just pick it out by choosing to multiply by a row vector that has just 1, 1 in it, and some column vector that has just 1, 1 in it. And the point is that this can then, you can easily see that this is bounded just by the condition number times the operator norm of E. Right? Because when I multiply EI by U inverse, that vector gets dilated by at most 1 over sigma min of U. And when I multiply U times EJ, it gets dilated by sigma max of U. So we end up pulling out this condition number, and then we're taking quadratic form of 2 scaled unit vectors, which is where we get this operator norm. So this is the sort of more precise bound that that tells you indeed as you have the control to push the spectral norm or all of the entries even in E down to 0 at some inverse poly rate. If you have some polynomial bound on the condition number, you're in great shape because you can make this error term be any inverse poly you want. That's the key point. So does that make sense?
Could you just repeat it again?
Yes.
So what do we have control over exactly?
So E, the way to interpret E is that this, in all of our discussions, is sampling error.
Yeah, that makes sense.
If you want to think about it as, the simplest version of this is, I have a coin which is p-biased, and I flip it, a polynomial number of times, and I look at the empirical fraction of, times that it's heads versus, that'll be p hat versus the true fraction. The more and more, p hat will never be precisely equal to p. You can't really say that with high probability, but they'll converge to each other at a very good rate. The same way that if you think about E as being sampling error from our models, because we're trying to estimate things like moments or probabilities of certain, triples of events happening, which is what we're going to do when we apply this, we drive this to 0 at some inverse poly rate with our samples. Whatever poly bound we have on our condition number, that's fine because we can overcome it by making E comparably small. The norm of E, yep?
In practice, the condition
condition number has no reason to be polynomial. In fact, it will be exponential number in the size of the input. If you like,
why?
unless we make this assumption. But
Sure, but you know, if you think about it this way, right? So what did we do last time? So we talked about if you have exact access to the moments and it's full rank, then you can do everything, right? And we also gave this result that if it's not full rank, then you're in trouble because it's like cryptographically hard, right? Because of, you know, noisy parity. This is really, you can think about condition number as being a smooth way to interpolate between the two. That now when you talk about not having exact access to the moments, well, what you need is not just full rank, but you need some reasonable bound on the condition number. If you don't have that, you're very close to the same issues, which go wrong with being degenerate in terms of your rank anyways, that force you to sort of have cryptographically hard problems. So, you know, if you think about, you know, U, for example, as being factors in some, you know, topic model, right, as they're the sort of columns in a topic matrix, you wouldn't really expect this to be exponentially large, I don't think. That would be sort of two topics that are, you know, extremely hard to distinguish, would be one way of thinking about it. But that's the way to think about it here. So, any other questions about this?
Wait, I insist on another question. So, sorry, Anchor.
Okay.
But I thought like, maybe, I don't know if this is the wrong way to think about it, but like when we have access to M, it's like we get a sample of M tilde, no?
What do you mean? So M...
Like M is the truth and E is the error. That's just it.
Yes, yes.
And, but
so M is the truth. We're going to see how to apply this, but I just want to make sure you guys understand how we're going to do it before we do it, because this will tell you which of the pieces we have control over. M are the true moments, but you can only estimate those. So all you estimate is M tilde. You take more and more samples, your error between M tilde and M becomes small.
So when you say you take more samples, you mean you take more M's or more rows of M or more columns of M? What do you mean exactly by that?
Think of this as like the entry in ij is the probability that some variable is I and some other variable is j. So as I take more and more samples, I'm getting better and better empirical approximations to what those moments should be, which means error is driving down.
Okay, that makes sense.
The dimensions of these matrices are not growing. It's as I'm taking samples, I'm driving this error down.
That makes sense.
All right, good. Any other lingering doubts? All right, so just to finish this argument now, so what we're saying is, so we're really saying in all of this, as E goes to 0 at some inverse poly rate, then the max entry in F goes to 0 too, at an inverse poly rate as well. That depends now on the condition number of U. And by Gershgorin, it implies that the eigenvalues of M tilde are contained in disks centered at the entries in the diagonal, right? Because that's what the dominant term is in this bound, whose radii are converging to 0 as well. So that's the geometric picture, right? Is that Gershgorin then tells us bounds that, you know, this F is what controls the radii in Gershgorin's theorem. F is going to 0, so our radii are going to 0. And the dominant term will just be the entries along the diagonal. Those will be the centers of the disks. So the point is, whatever your separation is between the centers and your disks originally, so what the separation between your eigenvalues are originally, if the radii are small enough compared to that, those disks will be disjoint. Hence, they each have one and only one eigenvalue, which implies that the entire matrix is diagonalizable. Right? Because it means that they also have distinct eigenvalues. That's the key point. So hence, if E is small enough, and you can work out exactly what the bounds are, but the important point is compared to some fixed polynomial and 1 over n, 1 over the condition number, and the minimum separation in eigenvalues in D, then M tilde is, has distinct eigenvalues. And is diagonalizable. So it's a very simple application of Grishkorin's theorem. But you see how we needed the extra power of Grishkorin's theorem, because the original part of, the first time I taught this, I actually omitted this part, and that's a mistake. Because if we didn't have this part right here, all we'd be saying is that the eigenvalues are contained in the unions of these disjoint disks, but that doesn't mean there couldn't be more than one in one of the disks. And maybe those eigenvalues just happen to be the same, and then that wouldn't be a strong enough conclusion to necessarily conclude it's diagonalizable. But the fact that Grishkorin's theorem can be strengthened to the statement that when the disks are disjoint, each disk contains one and only one, that's enough to guarantee us then that M tilde has distinct eigenvalues. So that's the point. Any questions about this? This is just part 1. Who's ready for part 2? All right.
Isn't it that M tilde in the algorithm is itself a symmetric matrix?
No, that's a good question. So in some of the things we do, it will be symmetric. If you think about applications to topic modeling, where you have, the first 3 words, those 3 words are interchangeable in any order. So, the tensors themselves will be symmetric, as will the matrices be. But if you think about things like phylogenetic reconstruction, where we thought about the tensors as being the conditionally independent random variables on the leaves, those leaves can and do have different distributions. And the tensors are not necessarily symmetric, and the matrices are not necessarily symmetric.
In the algorithm, we're computing the singular eigenvalues of when we hit...
Computing the eigenvalues.
Yes, but eigenvalues, okay.
Eigenvalues, not singular values. All right. Yes, let me do part 2 over here. Okay, so let's do part 2, perturbation bounds for eigenvectors themselves. So now the nice thing is that we can just say that M has an eigendecomposition, and now our goal is to check how close that eigendecomposition must be to that of M's, right? So, to that end, let's do the following. So to that end, if you see from part 1 that as we drive the error down, well, not only so those disks are disjoint, so there's a natural coupling between the eigenvalues of M tilde and those of M. So we can really talk about a pair of them. So let's say that we have them paired so that lambda tilde I is close to lambda I. That's the closest one to it. And what we want to do is we want to then analyze how close these two guys have to be. So there's one, last trick in sort of analyzing this. So the sort of nice trick is that it makes sense to think about representing the eigenvector for m tilde in the basis of the eigenvectors for the other guy. And what we really want to reason about is we want to reason about the CJs where J is not on. We want to show that if any such CJ has to have very small value that we can drive to 0. And that'll be enough to show that really U tilde I is close to UI because they're normalized the same. They'll still have the same unit norm. They're unit vectors. So if we force all of the other things to contribute almost nothing, everything has to come from UI. So that's the basic idea, yeah?
So how do we know the U tilde is expressible in that way?
Because they're both spans. They both span R. So, I'll say something at the end that the way we talked about Generick's algorithm the first time was with pseudo inverses. Everything becomes more complicated there because then I have to be talking about a restriction of Rn. So it's much easier to think about it with inverses where U really is invertible. Everything becomes even more hairy as soon as you don't assume that, but they still work. So we know that this holds just because this is a basis. So now the key idea is let's do the following. Let's just multiply by m tilde. And we can rewrite this now as we get, lambda I ui, just by the definition of the fact that it's an eigenvector for m tilde. But now the important thing is that we can also write it out this way, that we can break m tilde on the left up into m plus e. And the m part has really nice behavior with the uj's. So we just end up getting cj lambda j uj. But then we have an extra e term times u tilde I, right? All this is just this vector, and we break up m tilde into m plus e, and m has a really nice action on the uj's. So now what we can do is we can write this all out in another way, and then we're almost done, is we can write it out as cj times lambda j minus lambda I tilde uj, and that just equals minus e times u tilde I. Right? We're just using what u tilde's representation is again. So the key point to all of this is that what we can do now is we're going to let wj be the jth row of U inverse. And then what we know is that wj transpose times ui is equal to 1 if I equals j and 0 else. So this will be the vector that will allow us to reason about a particular term, cj in here, is that if you think about, this is a semicolon, if you think about the jth row of U inverse, right, whatever that row is, when we multiply it by U, it's just going to get a basis vector, which has only one non-zero, which is where I equals j. That's it. So this is going to help us here, because what we can do is if we left multiply this entire thing by wj, what we're going to get is that we're going to kill all but the uj term right here. So we're going to end up with cj lambda j minus lambda I tilde equals minus wj transpose E U tilde I. So I claim this is exactly what we are looking for, right? The way to interpret this is that we get to drive E to be small. We have some lower bound on what the separation is, because all the lambda j's are somewhat separated from each other, and lambda tilde I is close enough to lambda I that we also have a lower bound on what their separation can be. We divide through and we still have something that we can drive to 0, which tells us each of these coefficients Cj is small. We can do this for any j not equal to I, because that's when we have a lower bound on what this magnitude can be. So what this implies at the end of the day is that Cj goes to 0 for all j not equal to I, and hence we get that the eigenvectors converge. Now this convergence at an inverse Pauli rate, it depends on what the minimum separation is. It depends on the condition number of U again, because that'll tell us what the norm of W is, for example, as a unit vector. And it'll depend yet again on the spectral norm of E. But the same things that governed part 1 govern part 2 as well, that we have convergence in eigenvectors. That's the end of part 2. Right? And you can see that if it weren't 10:15 in the morning, that I could calculate all of these if I wanted to and get really painful expressions for how the things relate. That's not important. The important thing is just the qualitative property. So now we can apply it to tensor decompositions, but this is what tells us that eigen decompositions themselves are well behaved. Any questions about part 2? Who's ready for part 3? There's no part 3. I told you the plan. All right, let's apply it to tensor decompositions. So now let's not forget where these is there a question? So now let's not forget where these tensor decompositions came from. Let's think about one canonical problem and think about how the types of bounds we're proving come into play there, right? So as a canonical example, or you can feel free to choose any other example we've done, because that'll give you a good exercise thinking about how these perturbation bounds apply equally well there. But as a canonical example, suppose we just have this really simple phylogenetic tree, where we have this hidden root, and then we have these 3 observed leaves, which are which we see the states on. And the way that we applied our tensor decompositions was that we set Tijk to be equal to be defined as the probability that the state of A is I, the state of B is J, and the state of C is K. And now what we really cared about is when we can't exactly compute that quantity on the right-hand side, we can only estimate it through random samples. Well, we also had this property that this tensor, the way it was defined, was exactly some low-rank tensor because these guys are conditionally dependent. That was the key point that we exploited. We used the fact that it takes this form. That it really does have a low-rank decomposition. And now the way that we compute our estimate is in the obvious way, right? All we do is we let Tijk be the number of samples where S of A equals I, S of B equals J, S of C equals K, and then we divided it by the total number of samples. So this was our empirical estimator for T tilde. And the way that we wanted to bring all these perturbation bounds to bear was we wanted to know if we only have a reasonably good approximation, T tilde to T, what does that tell us about actually learning the parameters of our model? That's the way the estimators we designed really work, and we care about, do the estimators we designed converge the true parameters at an inverse polynomial rate? That's what we cared about. And so now we can think about each of the steps in the algorithm, what it looks like in terms of our perturbation bounds. Now, the most obvious thing that I'm sure, or at least I hope all of you know, is that T tilde converges entry-wise to T at an inverse poly rate. And I'm going to use this symbol to denote that, the way I've been doing it throughout. And we're going to say that this happens if, the way to think about this is that for all epsilon, there is some little m, which is some polynomial in 1 over epsilon, where with high probability over m samples, we're entry-wise close on every single entry. So T tilde is converging to T at an inverse poly rate, because when you tell me your target accuracy, I give you a polynomial bound in 1 over that accuracy. Now, in general, the other things that we talk about convergence may depend on other properties as well. Some of the other convergence bounds depend on the condition number, some depend on 1 over the mid separation. But I'm going to use this notation to sort of mean the obvious thing, that if all of those parameters are reasonably bounded by some polynomial, that we do have this type of convergence, that we only need poly samples. Okay? So now let's apply it. Let's think about Generick's algorithm and the different steps. There'll be one trick, but that's about it. So if you remember, we had T tilde A, well, we had TA, which is just what happens when we choose a random unit vector A, and we collapse the tensor along some direction by summing it according to A. And so we were just creating a matrix out of a tensor by flattening it according to A. And what's also obvious, I claim, is that T tilde A converges to TA. That's kind of clear, because if T tilde is close enough to T, then there's no way that a flattening according to a unit vector can be all that off from what the true flattening should be. That's simple. And it's also obvious by the same token that you have this type of convergence. Now it gets more interesting. There is one last trick. If you remember in Generick's algorithm, there was this key step where what we looked at was we looked at TA, TB inverse and things like it, because we cared about an eigen decomposition of this. Now, what we have shown so far is that if we get close enough estimates to a matrix, then there are nice conditions under which its eigen decomposition converges to the true one. But at the end of the day, one of the things I need to prove is still that TB TB tilde inverse converges to TB inverse. And that actually, there is a trick, which, the way that I'm going to think about it is, hopefully you guys all know the following identity. Right? Brando's laughing because we did this in 042. But actually you can do it so it holds for matrices too. So that's the cool part. Of course, it has a different name. So it's called the Neumann series. And all you have is that if you take the identity plus some perturbation A, and you look at its inverse, that you can actually explicitly write this out. Remember that, Gershgorin's theorem was a way to show that the eigenvalues are close to the eigenvalues with what they should be when we take I versus I plus A. But actually, the Neumann series gives us a way to analytically write out what this inverse is. So all it is it's sum from I equals 0 to infinity of A to the I, with the obvious interpretation that A to the 0 is the identity. So if you think about this perturbation as being small enough, then all but the first term are bounded in their contribution. This again only holds if A is small, but here instead of needing a condition on the magnitude of X, you need a condition on the operator norm of A for this to be true. But now I claim we're actually in great shape.
And it's a plus? I plus A? I'm just wondering.
Yeah, maybe it's that. Maybe I messed that up. I have to double check that.
Let me Google it.
That's what I have down here, but yeah, check it and tell me. It doesn't matter too much because it's going to change whether we add or subtract our error terms, so not a big deal. But now to sort of finish up, what's going on is that we have T tilde B equals TB plus some error. This is a different error than before. Then what we can do is we can just look at the quantity we'd like to show converges. And this literally is just this. Now the remaining trick is that we can actually pull out a TB inverse and look at it as I plus TB inverse times E, all inverted. So the sort of key point is that when you look at this series and you plug in this term for A in here, well, if E is small enough, and now that also depends on what the minimum singular value is for TB, that if E is small enough, then again, only the first term will dominate, which is the I term. So what that'll tell you is that TB tilde inverse converges to TB inverse. That's the remaining step here. Of course, this convergence now depends on what the minimum, singular value is for TB inverse, but this tells us exactly what we wanted, that we actually have this type of convergence. And now what we proved so far for eigen decompositions is that if we have a good enough estimate to the thing we want to eigen decompose, then what it really tells us is that our eigenvectors also converge, and that's why our factors, we learn them. And that's why the estimators that we have actually converge to the right answer at an inverse Pauli rate. Of course, you have to take into account a lot of parameters for what that really means, because there's all sorts of min separations and smallest singular values and condition numbers. But under reasonable conditions, all of the things I was telling you were actually honest, and I wasn't trying to cheat you intentionally, is that you can turn these into algorithms which can even work with reasonable sample complexity. Now, it takes a lot more work to sort of get the right balance for sample complexity, but this is, I think, the easiest way to think about the qualitative issue of why do they have polynomial sample complexity. Does this make sense? All right, so what we're going to do is we're going to take a 5-minute break so that you guys can digest this. Then, actually, I'm going to take Ariel's question first.
Then, yeah, it says that it's minus.
What?
It should be a minus.
It should be a minus. Okay, good. That makes sense, especially when I choose A to be a scale of the identity. It better be true that I recover the same identity. Anyways, so let's take a 5-minute break so you guys can ask me any questions about this. Then I'm going to tell you actually, I mentioned at the very beginning that it took me a while to figure out who originally discovered the simple tensor decomposition algorithm, which has so many uses. It got rediscovered, I think, in every decade. There's actually a sort of fun story about why I think it was forgotten, which has to do with an open question. So I'll tell you about that after the break.
Anchor. But the generics algorithm uses the pseudo inverses, right?
Yes.
Does that
So
make
these
things a lot hairy?
A similar analysis works, but it really does make it hairier in terms of doing the full analysis. Because if you think about it, then you're really, you need another statement that instead of saying that the UJs that I'm interested in span the space, they don't span the space. They span something close to the space you really have. So what you really need to do is you need to project onto what are the large, you can estimate just from M tilde what the span of those are, if it's close enough. And then you really need to work in that related space, which is not quite the true space. So all the things go through, but it has this extra complication that you need to work in something that just has a very small angle with the true subspace.
And there's
Okay.
which is also the end of part 1, I think, which is why we're, so end of.
Because most of my questions I was going to ask you were about
Pseudo inverse?
that pseudo inverse stuff in the algorithm.
Right.
But
So-
I guess you kind of already explained it in a analogous setting with in the inverse.
Yeah, exactly.
Which is
so
just-
if you want to think about the inverse only, one of the things I can do, just not the optimal thing to do, but just to think about why it works and shouldn't have an issue, is if I take the tensor and it has rank R, so they're not actually span the entire space, but they span some R-dimensional space. If I take random R unit vectors and project into their span, they will be full rank and they will span that space. And then I can just do everything with inputs in the restricted space, and I can ignore all the complications. But that's actually forgetting some of the information, so it's not the right thing to do in general, but it's the easiest way to think about why you shouldn't have an issue. It's this.
Can you explain the limitations of this whole analysis? So one was the span of U has to be the whole space.
This construction is
Are there
So all this stuff works, even if you're using pseudo inverses instead of inverses.
Okay.
It becomes more complicated to actually analyze it, but there aren't big qualitative differences.
But are there other limitations like that?
No.
Okay.
Yeah, I mean, it's just that when the U's don't span the space, what you get is the span of the things you have has a very small angle to the true thing. And what you need to do is you just need that complication that what you're working in has a very small angle compared to the true space, and then you can push through the errors that way. But it doesn't actually change any of the,
Yeah. So
it just adds more steps to the analysis, but the results are roughly the same.
Yeah. So when you want to apply this, for example, you don't have to check anything on your data first.
But if you want to apply this, the right thing to do is to, if you don't have the U span the space, what you should do is you should estimate your matrix, your tensor, so well that the small eigenvalues and the directions which correspond to them, you can throw away because those are just noise. And then you work in the restricted space. So that's the point, is that all of the stuff here, you can still do with pseudo inverses.
It does, but
The algorithm is slightly more involved to state, but the analysis works almost verbatim.
Yeah, but there was another one that
it also
Oh, maybe
that the condition number U cannot grow too big, right?
Right, but then it should be,
Yeah, so that's what-
the max to min eigenvalue for that guy ignoring the zeros. So if you look at just the space spanned by the U's you care about, that space, it should not be that different between its largest operation on a vector and its smallest.
So
And that's what you
that's
get.
somehow how it is.
Yeah, exactly. Is that you should be able to focus on just the parts you care about and do the same analysis, but it's more painful. Yep.
So in applying Gersh scoring theorem, can we use the fact that the eigenvalues of A transpose is equal to eigenvalues of A, and maybe take the intersection of two spaces that they make?
So to what end, though? To get better convergence bounds?
Yeah, maybe better specification of the disks, right?
Uh-huh.
Because then the intersection is going to be smaller than either of them.
Yeah,
So,
I mean, even then, Grishkorin isn't even the tightest thing, because there are ways to do it with ellipsoids, which are slightly better. But,
in the current way that we define it, I think, yeah, my intuition says that they can be different. If we define it, for A.
You want to chat more at the end? That's a longer discussion, because I think, so this is my summary of an entire field, because this is matrix perturbation theory. And this is just the parts that I like to remember. Has it been 5 minutes? It's close enough, right? All right. Okay, so you remember that when I first introduced tensor decompositions, what I told you about was Spearman's hypothesis, this rotation problem. Spearman's hypothesis was that there are two types of intelligence, and he wanted to verify his hypothesis from just this matrix of how students performed on different tests. But one of the issues is that matrix decompositions are not unique unless you add extra features like non-negativity and separability, or on the other end of the spectrum, something like orthogonality between the different features, which is a very different type of constraint. And the reason we got into tensor decompositions was because we wanted to have uniqueness and now robustness results as well by virtue of these perturbation bounds, which applied to settings which were less stringent about what they impose on the factors. So actually the place where Jenrick's algorithm was discovered, it was discovered, it was stated in the paper of Harshman, but it appeared in the psychometrics community. And the funny thing is, when this paper appeared, I think partially the reason it was forgotten was because there were better uniqueness theorems that were proven later that don't have algorithmic versions. So the fact that Jenrick's proof was not only a proof of uniqueness, but it was an algorithmic proof of uniqueness is very important for the applications, but that entire field didn't really have the language for explaining that what's important is not just the uniqueness, but that it comes hand in hand with an algorithm. So there's actually one question, which is the uniqueness theorems that are known beyond Jenrick's uniqueness theorem don't have algorithmic counterparts at this time. So, one of the famous ones is called Kruskal's uniqueness theorem, also in the psychometrics community. And the key notion is that first I need the notion of the Kruskal rank. So I'll call it the K rank of a set of vectors ui is the largest R such that all sets of R vectors, from UI are linearly independent. So I'm given a set of vectors, and I want the property not just that the span of all of them covers all of space. What I could want is maybe even a stronger condition, something like every n of them also spans the entire space. So that's oftentimes called general position. So the usual reason for this nomenclature is that if you sample a ton of points, as many as you want, n squared, whatever, exponentially many, well, they indeed are in general position in the sense that every n of them will be linearly independent, almost surely. And so Kruskal's uniqueness theorem makes use of the Kruskal rank. So you remember that Jenrick's algorithm only used the fact that the factors u sub I were linearly independent, the fact that the factors vi were linearly independent, and some condition on the w's. But that itself has the stringent requirement that the only way that you can get away with that condition being true is if your number of factors is at most n. Well, it turns out by imposing stronger conditions on the set of vectors, namely that their Kruskal rank is large, that you can actually get away with r's that are beyond n and still have uniqueness theorems. So let me state Kruskal's uniqueness theorem. So we have our tensor decomposition, which is now we're going to be interested in cases where the rank is not n, but is larger than n, like 1 plus epsilon times n. And what we're going to do is we're going to say that Ku is the Kruskal rank of the u factors, Kv is the Kruskal rank of the v factors, Kw is the Kruskal rank of the w factors. And what he showed is that if Ku plus Kv plus Kw is at least 2r plus 2, so you remember that we have all the usual caveats about the uniqueness of the tensor decomposition, that you don't know the order of these factors because I is the same as I prime for all intents and purposes, and you can rescale these things in such a way that you preserve what the rank 1 term is. Well, all the usual caveats. And then it turns out that if Ku plus Kv plus Kw is at least 2r plus 2, then T's rank R decomposition is actually unique. So that's the sort of key point, is that this applies even in the optimistic case where you think about, the best Ku can ever be now is n, and same for Kv and Kw, and then it's actually going to apply up to about 3/2 n. So it's going to work for what are called overcomplete tensor decompositions because R is beyond n. So Kruskal's theorem applies even for R is about 3/2 n minus O of 1, meaning that it's still interesting in that setting. There are even robust versions of Kruskal's theorem too. And they show the usual things that, if you have some bounds on the condition number of the different factors, so some bounds on, not only should every KU of these guys be linearly independent, but they should be somewhat far from being degenerate, so you need some sort of lower bound. Then what they say is that if you have good enough approximation of T, that any decomposition is close to the true decomposition. So you even have robustness types of theorems, but there's no algorithm. So let me state the open question. So is there any efficient algorithm that works under any reasonable conditions under the factors? You can assume they're in general position if you want. You could assume that whatever factors someone has chosen get perturbed in a way that destroys any sort of pathological linear dependencies that could arise. And the question is, can you get an algorithm that works for over-complete setting? And really over-complete in the sense that you want to have some constant larger than n factors that you can deal with, even though generic only works for n. So that's the sort of question. And one of the real challenges here in the algorithm, I'm not sure this should be related to this, but one of the complications is that it's actually NP hard to compute the Kruskal rank. So that's a bit different than in generic setting. In generic setting, if I gave you the factors, then you could at least compute their rank and check that they really are full rank. And then you would know that your tensor really is unique, that the decomposition is unique. Now, one of the challenges is that actually even the condition Kruskal is using in this theorem, that he's imposing a stronger thing than just linear independence. He's saying every n of the vectors have to be linearly independent. That condition alone actually turns out to be NP hard to check. So that's one of the real complications with this theorem. So let me prove that for you, since I think we have enough time to do that. It's a pretty simple proof. It's funny that this result, the fact that it's NP hard to compute the Kruskal rank, is also something that got rediscovered a bunch of times for different reasons. I think by my account, it was an open question in computational geometry that was open 8 years after Kachyan solved it, but in Soviet Russia, where some of the math didn't diffuse over the country boundaries. So let me show you why this is. And the way that we're going to prove it is we're actually going to prove it for general position. So there's one sort of trick here, which, has anyone heard of the moment curve before? Yeah? All right, so the moment curve is usually what you do is you take a value, alpha is some real value, and what you do is you map it to a vector, which is just a vector of powers. That's why it's called the moment curve. So you map it to a vector in RD in the obvious way. Now, one of the nice things that you can do is you can then use this mapping to construct what's called the van der Waals matrix. Which you can construct as some matrix in RD cross D. So does the definition of the van der Waals matrix make sense? Yep.
Those are the different alphas for the bar.
Exactly. Well, not necessarily, but so the point is that the matrix makes sense, and the question you're asking as a grade 1 is really related to the question, when is this full rank? So this matrix, I claim you actually already know intuitively why it's full rank. Let me state the claim precisely. Let's call this matrix V. Then I claim that the determinant of V is not equal to 0 if and only if the alpha j's are distinct. So one side is easy. Definitely if you have a repeated alpha j, then you've got a repeated column, so there's no way that it's full rank. But actually I claim you already have intuition for this, even if you think you don't. So imagine that I left multiply this van der Waals matrix by some vector. Right? So let me write out what that looks like. Is we left multiplied by some vector p0, p1, up to pd minus 1. Then what I'm claiming is that we can actually think about this as being a polynomial. In just the natural way that the first coefficient is the constant term, the second one is the linear term, all the way out to d minus 1. But the key point is when I multiply this vector times the van der Waals matrix, what I'm actually getting is I'm getting the evaluation of p at alpha 1 and alpha 2 and so on. And so the point is that when can if I take any polynomial of degree d minus 1, so it has 0 to d minus 1 are its terms, then if I evaluate it at d plus 1 locations, it's uniquely determined, so I can recover. So in fact, you guys already know a way to solve this linear system, which is what tells you that it is full rank when the alpha j's are distinct. So that's fine, right? They look not intuitive the first time you see it. And actually, let me make a further claim, which this one takes a little bit more to verify. But it turns out that its determinant, one of the reasons it's useful is that its determinant also has a really nice expression. That its determinant is expressible as the product over all I less than j of alpha I minus alpha j. So this is sort of just the standard background on van der Waals matrices. And this is something that you can check with a little bit of work. One way of thinking about this is that we already know that if some pair of them are the same, its determinant has to vanish. And actually, we can figure out what its degree is in these alpha j's. And we know it's a homogeneous polynomial, and that's the sense in which it really has to be that. But now there's something you can do, which is weird, which is called the weird moment curve, which is how you can prove that Kruskal rank is hard to compute. This is what Kachyán did in a paper that's also forgotten for some reason. So you do almost the same mapping, but there's one distinction. That at the end, you increase the power by 1. That's it. That's what's weird, right? So it makes sense. Still degree d, still length d vector. But instead of having a d minus 1 at the end, you jump up by 1 more. Now, this also leads to a weird van der Waals matrix. In the obvious way, we have these different values. It's just that at the end, we have d minus 2, and then we go to d. And we do the same thing. But now what I claim is, let me call this v prime. Well, if you think about it, the determinant of v prime is also going to be a polynomial in the alpha j's. That's for sure. And again, we have this property that if 2 of the alpha j's are the same, it's going to vanish, for sure, right? Because we'll have a repeated column. So whatever this determinant is, it certainly has to contain the determinant of the van der Waals matrix as a factor. But maybe it has something else that's multiplying this factor as well. In fact, if you think about this determinant, well, each term, you're going to choose a configuration of entries so that there's exactly 1 in each row and column, and then multiply them. And all that's going to happen is each term has 1 larger degree. So you have some degree of this polynomial, but the missing factor has to be something that's a linear factor as well. What should it be? It's later than 9:30, so
Some of alpha i.
some of the alpha i's, exactly. That's the missing factor. Okay, now we're almost done. So let's prove the NP hardness. The idea is what I do is I give you a collection of numbers, real numbers, where n is, larger than d. It'll usually be a constant factor larger. But what's a hard problem is determining whether there's exactly d of them that sum to 0. We actually already talked about this problem. It's called d-sum. In the case where d is large, then it really is NP hard, and you can't do it in end of the d time with the exponential. But we already talked about this problem, and now we can, we talked about it when we talked about hardness for NMF. But in the same way, it gives us a way with this mapping to create hardness. Because what we do is we apply this weird moment curve. So each alpha I goes via the weird moment curve to some vector, v alpha I. And the point is that the k rank of these vectors that we create out of here is less than n, less than d, if and only if there exists a set S of size d where the sum of the alpha i's for I and S is equal to 0. That's the point. By construction, these guys are distinct. So if there really was no set that summed to 0 here, any way of pulling out which of these vectors, well, you would get this determinant polynomial, which this is non-zero because they're distinct, and this is non-zero because it's not a satisfying set. And in the obvious way, if you really did have a set that summed to 0, then you can see just from this determinant calculation that it really would be not full rank and would have a linear dependence. So this is the sense in which if I give you n points in d dimensions, but you're thinking of n as being large compared to d, like 2 times d or something, so that you can't afford to just brute force search, then dsum really is NP hard, and hence finding whether or not a set of points in general position is also NP hard. So this is what I think puts Kruskal's uniqueness theorem in a slightly different category, is that it's actually invoking a condition which is hard to decide whether it holds or not. So there are lots of other uniqueness conditions, ones which robustness guarantees are not necessarily known. Like if I choose a random third-order tensor, I can actually have it be unique up to about a quadratic number of factors, just by basic statements about algebraic systems. But the issue is that for all of those things, we don't really have nice conditions that imply uniqueness. Even in the case of Kruskal, the condition is nice to state, but it's NP hard to decide. So I'll stop there if you guys have any questions. The one thing I do want to mention is that we're going to use this hardness result in other cases. One of the things that you can get for free out of this is if I took this weird Vandermonde matrix and looked at its kernel, what this is really saying is if I give you a subspace, it's hard to decide whether the sparsest vector in that subspace has d non-zeros or d plus 1 non-zeros. If they were in general position, you'd need d plus 1. And if they weren't, you could get away with d. But actually, I don't know of any better gaps in the hardness there about finding sparse vectors over the reals. So that's actually another interesting open question. All right. Thanks. Yeah, let me see if I can find that. Yeah. I've never found it as useful as the other things, but one of the annoyances is that if you look for, there are lots of nice theorems, like there's Whedon's theorem that tells you if I have, A plus E, the bound on the operator norm of E is what tells you a bound on the sign of the angles between the corresponding principal subspaces. So it tells you how much geometrically you can distort these things. Does that make sense?
The bound on the operator norm determines the sign of the angles?
SINE. So if you take, if you take a matrix, yes, exactly. So it determines the sign.
Okay, right.
That's Whedon's theorem.
Right.
And then there are lots of things like there's Bauer-Feiche, which is kind of funny because for Gershgorin, I needed the statement that if they're distinct disjoint disks, then there's one in each. The funny thing is, for example, like the Bauer-Feiche theorem gives you something that's similar, but it doesn't actually tell you the corollary that Gershgorin does.
Oh, okay.
So, which is kind of an annoyance.
Because we can never check if it's really diagonalizable.
Yeah, exactly, because you could still have two in one thing. So there's that technicality. So I would say that my understanding of matrix perturbation is that for the SVD types of things, or in cases where it's symmetric or has other nice conditions, it's very well understood they have pretty bounds. But as soon as you work to the full generality of generalized eigendecompositions, things become ugly, and there aren't those nice black box things that I know that you can state that imply all the things you mean. The best thing I know is that there's the Stewart and Son book from the 80s, in which what they considered was they looked at if you have two eigenvalues for one and the perturbed, they looked at if you project them onto the unit sphere, the chordal metric. So they defined a metric over, that doesn't take into account how dilated you are, but they have something there. But the only bounds I know that work in full generality are really ugly as you carry through all of these factors, which is kind of a pain. So all of those ugly bounds, I would say that there's huge scope for trying to improve them, because even in the case of Whedon's theorem, like this guy Van Vu was here a year ago talking about improvements when the matrix E is random. So there's a sense in which, if you sort of do the natural Taylor expansion, there's a setting in which you can get better bounds by looking at the second order things.
Yeah.
And if you only want to bound it by the operator norm, Whedon's theorem is tight, but there are stronger things that you can take advantage of for random.
Mm-hmm.
But the flip side is that at the very other end of the extreme with no conditions on the thing, other than things that you really do need, the bounds are so complicated that, you know, I'd be shocked if they can't be improved, but I don't know of nice bounds there.
So for this random case, random error case, we also need that kind of structure to give reasonable statements, right?
That's for the
symmetry
Whedon
or-
thing, you need that to give better statements than Whedon.
Okay.
So Van Vu has some paper that's up where he uses the random E to give better things than Whedon in some settings of parameters.
Mhm.
So I'd recommend taking a look at that and then.
Sure. And whenever we're comparing the empirical tensors versus the real one, we don't take care of, we don't care about the randomness, right? As far as I understood, I mean, we're giving statements on the bounded operator norm of the error. So we usually state things as with high probability. We don't.
It's tricky because, see, like the same way when I have two matrices, right? If my errors were really random, then obviously having a component-wise error and then thinking about how large the operator norm can be, that's very wasteful, right?
Mm-hmm.
But for tensors, the issue is you can't compute the operator norm. So then there's settings in which, like, it's not clear which bound to use. So the same way that random things behave nicely and you can certify them for matrices, for tensors it does go a bit out the window. So it's not as clear to me. Like you could see that depending on how I measure the error, then I could have different sorts of bounds. Some which give better control in other settings, but I don't know too much beyond the qualitative.
Thanks.
Yep. Oh.